Welcome to the second part of our explanation. It's trying to understand the gas laws from the perspective of individual atoms. In the last lesson, we focused mostly on pressure and devised an equation that gave us a look at what's happening on the atomic level. This is a quick review of that. What we said was if we had a box with individual molecules bouncing around the walls in all directions, the microscopic aspect of of pressure is going to be related to the force of those impacts on the wall. And what we derived is that the total force, because of the gas hitting the wall, is equal to the individual force of each collision times the number of collisions. And we were able to put that into a more intricate format here, where you can see the 2mv is kind of a momentum term that we got from applying the idea of impulse on the atomic level. And it's also multiplied by that number of collisions divided by the time in which the collisions take place, which is kind of a rate idea. In other words, how often the collisions are happening in a particular period of time. Okay, so that was just a review of what we came up with the idea of pressure. We'll find out that by developing this equation a little bit more, we can come up with a microscopic explanation of what the macroscopic idea of temperature means. And that's what we'll start with right now. We'll begin by looking at this number right here, which is the number of collisions. And we left this number undefined in our previous equation, and we're going to define it more directly right now. One of the ways to think about this is to take a portion of the entire volume and kind of set it apart, as we have in the drawing on the left. We'll call this delta V as being a portion of the entire volume of our gas. So one thing we can say, just as an approximation of the number of collisions we could expect against the left wall, is that number of collision must be equal to the total number of molecules in the gas times some ratio of the volume, the small volume of molecules that are close enough to the left wall to actually potentially hit it, compared to all the rest of the volume, where many of those molecules are much too far from the left wall to ever participate in a collision. In other words, this ratio of delta V, in other words, our small volume, compared to the entire volume of the box. Let's say our small volume had a proportion of 1 to the total volume of 1/6, then only 1/6 of the total number of molecules in the box would ever have a chance of hitting the left side. And that's a way, what we're doing is we're trying to narrow down this number for the number of collisions that are possible on the left-hand wall. We can narrow it down even a little further by just, again, making a simple approximation of all of the gas molecules in our shaded region. Not all of them are even moving to the left. Many of them are moving to the right. If we assume that it's a random, then we could say that only 1/2 of those molecules would ever get to the left wall to make a contribution to our net force. And so this is our kind of our first stab at defining the number of collisions that we could expect on our left-hand wall. All right, now we can add some detail to our equation. What we're going to do is take a look at this volume that we have indicated on the left-hand side and say that the shaded region right here we could define as the area. It's kind of like the cross-sectional area of that small portion of the volume that I've indicated. Furthermore, I could identify this side of that smaller purple box and give that a name delta X. And you should know that if I multiply these two numbers together, I get my delta V, or the small volume. And what I'll do here is just make a simple substitution. That area times delta X is equal to our delta V. Divide that by the total volume, and I've basically made a substitution and added a little more information to my equation. Let's continue that. Now this point is a little bit more subtle. Thinking about molecules that have a chance of hitting the left-hand wall, we'd say that because the amount of time that each collision takes is very, very small, those molecules have to have a sufficient speed to cross our little distance delta x. If they don't have, in other words, enough velocity, they will not be able to actually cross into that box and be able to hit the wall. Put another way, my delta x must be equal to a certain average velocity times the time it takes for a collision to take place. Now notice now that this gives us an opportunity for another substitution. Substituting over on the right, we get the relationship 1/2 the total number of molecules in the box times A times now our substitution, the average velocity of the molecules times the time it takes for each collision divided by the volume of the entire box. And what we've done here is we've just continued to add more and more detail to this number that we're approximating, which is the number of collisions that we could expect on the left-hand side of the box. Okay, that means we're ready for a substitution. Now this is going to get a little ugly, but I want you to stick with me because you'll see that this simplifies down to a very elegant result that should make it worth our time going through this derivation. And here we go. I'm going to rewrite our equation down below. The net force is 2mv nc over that delta t. Now, just for simplification, what I'm going to do is I'm going to move that number of collisions out of those parentheses and place it here. That allows me to more simply make this substitution. And the number of collisions is equal to 1/2 the total number of molecules in the box times our little area of our box times the velocity or average velocity times our delta t divided by, we've got multiple v's here, so be careful. The one on the bottom is the volume, the total volume of the box. And this is our relationship that we've been working for. But it's pretty complicated, so we need to do some simplifications. And these go pretty quickly. Notice we've got 2 of these. We can get rid of the delta t's. Notice that these cancel out. And notice that on the top I have 2 velocities multiplied together, so I can get rid of one and square the other. And that gives us our first kind of wave of simplifications. This allows me to rewrite our equation. Our net force is equal to the total number of molecules times the area times the mass times the velocity squared divided by the entire volume. Now we've got a couple more things that we can do with rearranging. And so we'll start with this right here, our area. We can divide both sides by that area here. And that should immediately give you the idea that we're making some progress, because we have just identified now the force or the net force divided by the area, which is the area of the side of the box. But we have another name for force divided by area. We have come back to the idea of pressure. So now what we have on the left-hand side is the macroscopic idea of pressure. Okay, continue to reorganize our equation. We've got volume on both sides, so I can multiply both sides for the volume, and I get something like this. Now what I'm going to do is you'll see why I do this in a second. It's a little slight mathematical sleight of hand, but I'm going to multiply this side by 2 and then immediately divide the same side by 2. So I really haven't done anything to that side, except it allows me to regroup like this, and you'll see in a second why this is interesting. And now we're done with our simplified derivation. Now let's see what this means. Let's see if it was worth all of this effort. I'm going to rewrite below here what we had above for the gas law. Notice right off the bat, this equation that we have developed for the what's happening microscopically inside of our gas has starting to take the form of our macroscopic gas law. Now notice right here that in the macroscopic gas law, it's PV is equal to NR, which is a constant that's related in the macroscopic to the number of moles. In our microscopic equation, it's related to the number of molecules, very similar sort of thing. And with the macroscopic calculation, obviously we have our final variable associated with T. PV equals nRT. Now hopefully you are noticing a parallel here, that the temperature from the macroscopic idea of the gas law is related to this thing in our microscopic version of the gas law. And that microscopic version of the gas law, 1/2 mv squared, should be familiar to you. That is a term for the average kinetic energy of each of the molecules in the gas. And that is what we have by carefully stepping through ideas of physics. In the first place, the idea of impulse and momentum. Carrying that through down on the microscopic scale, we've come to a representation of kinetic energy on the atomic scale. And that value, average kinetic energy, is associated with the macroscopic value of temperature. That is actually a surprising result. It's not something that we might have expected, but it's an extremely important discovery where we can relate this macroscopic quantity, temperature, and give it a good definition by having it be related to the average kinetic energy of the molecules that are in our gas. All right, that's the derivation that we wanted to do. We've just explored both pressure and temperature on the microscopic level. Thanks a lot for hanging with me throughout this presentation.